Okay, hello everyone. I'm going to present the four advance of my work entitled Study of the Liquid Phase and Liquid Vapor Coexistence of Mixtures of Nanostructure and Water. My advisor, the Dr. Minerva Gonzalez Melchor. To get back in context with work, as I mentioned, we use nanostructures. A nanometric structure is of the order of 10 to minus 9 meters, and this nanostructure can be classified depending on their morphology, like nanoparticles, nanotubes, and nanosheets. In this work, we focus on nanotubes. The nanotubes are characterized by having a Hamada index. This can be zigzag, armchair, or chiral. We conducted our study using boron-2 nanotubes, which were predicted by Rubio, Corker, and Cohen in 1994, since they have a structure very similar to carbon nanotubes. Boron-2 nanotubes have been proposed for different applications due to their properties, for example, in mechanical and electronic application, but also biomedical application. Some works have proposed nanotubes for the encapsulation and delivery of drugs, also for the transport of water through these nanotubes, and recently for the purification or treatment of wastewater. Most of these applications are developed in aqueous medium, so it is important to know the behavior of nanotubes in water, and this is the aim of this work. To perform this study, we use molecular dynamics, whose goal of molecular dynamics is to solve the equation of motion of the interacting particles in a system at successive instant of time. That is, we choose the ensemble, the interaction potential, and the initial conditions, initial positions and velocities, number of particles, volume, temperature, and pressure. Subsequently, the calculation of the force is made. For this, integration algorithms are used. The time evolution is performed to obtain the new positions and new velocities. At the end of the cycle, we perform an analysis of these results. That is, we calculate the physical properties of the systems. Molecular dynamics present its solution naturally in the macrocanonical ensemble. However, this is difficult to do experimentally. Therefore, a change of ensemble is made. We can choose, for example, the canonical or isothermal isobaric ensemble, in which it is required to maintain a constant temperature and or pressure. For this, molecular dynamics makes use of thermostat and barostat that help us keep these properties fixed in systems. To develop these studies, there are several simulation packages, so we use the GROMAX package to do all the simulation. And now, the force files are used to describe molecular interaction. The force file is the mathematical equation that describes the interaction and all the parameters that involves. Here, here we present the total potential energy that we use to describe the interaction in the mixture. It consists of two parts: intermolecular interaction, the bonds, the angles described by harmonic terms, and intermolecular interaction described by van der Waals and electrostatic terms. In our case, we have four different atoms, and to consider all the intermolecular interaction, we use a combination rule, has the inferior equation. Now we need the parameters necessary to the model water molecules and nanotubes. These parameters are summarized here. For water, they are used for the SPC epsilon model, while the nanotube, we take them from the literature. And the present some parameters found in the literature for the nanotubes, such as Garcia Toral and collaborators used for dopamine and caffeine encapsulation within boron-2 nanotubes. Kumar and collaborators to explore the properties of the monolayer of water molecules confined between the true extended surface, and Thomas Orgon and collaborators for the water permeation through boron-2 nanotubes. So in this work, we use a zigzag type nanotube whose index are 060, and the length of the nanotubes is 15.91 angstrom, and also the parameters considered by Garcia Toral and collaborators. So we present our free results of nanotubes in explicit water. For this, we perform simulation on the MPT ensemble, where we have used the Berensen thermostat and barostat. In addition, we vary the concentration of nanotubes in water, so our results are for three different concentrations. In figures, we show a snapshot of the system for the concentration of 0.11 mol per kilogram at 300 Kelvin and 1 bar. The figure on the left is the system in its initial state, while the figure on the right is after the simulation. After running the simulation, we calculate some properties of interest. In our case, we calculate the radial distribution function because it provides information about the structure and average distribution of the molecules in the system. Thus, we can see the effects of the concentration of nanotubes in the system. In the case of boron atoms, the peaks of the function are mainly generated by atoms of the same nanotube, but we notice that as a concentration increases, the values of these peaks decrease. This is because has an increase in the number of boron atoms, and this increase causes the boron atoms to be further away from each other. A behavior similar is observed for the nitrogen atoms. So furthermore, as we have set the pressure at 1 bar, and for this to maintain it, the volume has to increase as the concentration of nanotubes increases. On the other hand, with water molecules in the mixture, we observe for oxygen atoms, there is a slight increase in the radial distribution function. That is, the water molecules are closer to each other when increase the concentration of nanotubes. Otherwise, as it was the atoms of nanotubes. Now we calculate the correlation between atoms of the nanotubes and water molecules, and as can be seen in the figure, this correlation is very low. Moreover, if the concentration of nanotubes increases, this correlation decreases even more, since the volume increases to maintain the pressure constant, thus generating an even greater spacing between the water molecules and the nanotubes. Another, proper, Another property that we calculate is the static dielectric constant. This is calculated by the fluctuation of the dipole moment of the system. As water is a polar molecule, it has a high value of the electric constant. The experimental value is 78.5, and the one obtained by numerical simulation is 79.32. This value is obtained in this work, and it is 1% larger than the experimental value. So now we calculate the value of the electric constant for the mixture and compare how much it changed with respect to pure water. In general, we observe an increase in the value of the electric constant, since the charge distribution in zigzag type nanotubes is a dipole. Since in the nanotube each atom has a charge and forms a dipole, the interaction between water molecules and nanotubes are in the form of dipole-dipole. As can be seen in the top or right figure, if we have different charge, the interaction is attractive, while if the charge is the same, we have repulsive interaction. So the interaction of the nanotubes with the water affects the dipolar arrangement of the molecules. That is why the increases the dielectric constant is observed. Another part of result is the liquid vapor coexistence. May do simulation in MBT ensembles. To keep the temperature fixed, we use the nozzle-Hoover thermostat, and we also consider three different concentrations. For each concentration, we perform several simulations at different specific temperatures. As we show in the figure, the first located upper right part is the capture of initial configuration for the concentration of 0.22 mole per kilogram. The following image is when the simulation is performed at 300 Kelvin, thus having a dense region which is a liquid phase, while the less dense one is the vapor phase. The last figure is for the temperature of 500 Kelvin at which we can observe more molecules in the vapor regions. To obtain the coexistence cube, we first compute the density profiles of the different simulations at the specific temperatures. This is done using the slab method, which consists of slicing the cell into different slabs and calculate the density. In the left figure, we show the density at different temperatures along of the cell in the zeta direction. For the concentration of the 0.11 mole per kilogram, each of these curves contains the contribution of the density by the water molecules and nanotubes. As can see in the right figure, the upper figure is a snapshot of the system for the 400 Kelvin, and it is graphic of the density profile. We observe the contribution of the water molecule. It is the red curve. The green curve is the contribution of nanotubes, and by adding the two contributions, we get the black curve, which is the density profile of the entire system. Also, by adding the two, also it's important to mention that at temperature less than 550 Kelvin, the nanotubes are near of the interface, but at superior temperatures, the nanotubes tend to unite and stay in the liquid regions. After the compute the average density of each region and plot the values obtaining the coexistence cube. This is done for the different configuration to build the coexistence cubes as shown in the right figure. The black curve is the experimental coexistence cube for pure water, and the pink curve is taken from the literature while the brown is calculated in this work, but calculated numerically. So we compared our results of the mixture with these values. The blue curve is for the concentration of 0.028 mole per kilogram, which at temperature less than or equal to 550 Kelvin is very similar to that of pure water. Only at higher temperature there is a small increase in the density. This is due to the nanotubes that increase the density. In the red curve, it is for the next concentration. In the liquid branch is displacement since the concentration of nanotubes increases and the density in the liquid region increases. And to the highest concentration in the liquid branch, we notice the increase in the density due to the nanotubes. However, in the vapor branch, also the density increase, as can see in the right figure. Now we show the equation of pressure tensor component used in molecular simulation. It has a kinetical contribution that arises from the linear moment of the particles, where m and v are the mass and velocity of the particles respectively, and the second term is a configurational contribution that arises from the central force between them. The beta projection of force between a pair of particles I and G separated by a distance r is given by minus the chain of the potential. An element of the volume in a fluid has 9 components of the pressure acting on it, but due to the symmetry in the system, only we have 3 components in the diagonal. In our case, we have a simulation cell or leg L theta and transversal area A equal to Lx Ly. The normal direction to the interface is chosen in zeta direction. Then we calculate the components for the 3 different concentrations. As can see in the cell simulation, we have symmetry in the direction x and y. So the components px is equal to py and p theta is greater than 0. For the first concentration, we can observe that it satisfies the previous condition, but the second concentration was only at 650 Kelvin is not satisfied due to the concentration of nanotubes. This also can observe in the highest concentration, the component px is not equal to py due to the high concentration of the nanotubes. We also calculate the surface tension given by the terms of the normal and tangential components of the pressure tensor. The direction normal to the interface is the leg zeta. As we see in the figure on the left, we have the less dense regions that are part of the vapor phase, and the one that is denser is the liquid phase, and the little region where we go from the one phase to other is the interface. So we calculate the surface tension for the 3 concentration and compare them with the surface tension of pure water obtained in this simulation work. We observe that as the concentration increases, the surface tension decreases, is to say that the nanotubes favor the movement of water molecules from the liquid phase to the vapor phase as the temperature increases. A concentration of 0.025 and zero point 0.1 mole per kilogram, the surface tension values are on average 5% and 16% lower than pure water. This is due to the low correlation of nanotubes with water, so in terms of interactions, nanotubes reduce the cohesion energy of the water molecules. Also, because nanotubes are charged, they tend to align in a particular direction, and the interaction with water molecules is repulsive. This is most obvious at highest concentration, where the surface tension decreases even more. This is due to the large amount of nanotubes. So at this concentration, we say the mixture is saturated by nanotubes. Finally, our conclusions are in the liquid phase, at ambient pressure and temperature, we observe a low correlation between nanotubes as the concentration increases. Also, the correlation between nanotubes and water due to the increase of nanotubes in the mixture, and at the same time, the system increases its volume to maintain the target pressure. We observe that the value of the static dielectric constant increases because the zigzag nanotubes have a non-zero dipole moment, and the interaction between water molecules are of dipole-dipole type. So this could induce an orientation order in the dipoles of the water molecules. Further analysis is needed to investigate this point. Now, from the simulation of liquid vapor coexistence, we observe that nanotubes tend to recede at the interface and also facilitate the displacement of the water molecules from the liquid vapor to the vapor phase by increasing the concentration of nanotubes. And the surface tension decreases with increasing the concentration of nanotubes in water. This effect is important in application where the surface tension is an important parameter. We acknowledge Vicerrectoría de Investigación y Estudios de Posgrado, Laboratorio Nacional de Supercómputo del Sureste de México, and Consejo Nacional de Ciencia y Tecnología. Thank you.